Today we're going to focus on even a more specific picture of where our electrons are located in Concept H, where we're going to be focusing on how to write and interpret orbital diagrams. So students should be able to demonstrate how the sublevels are divided up into different orbitals, be able to draw and interpret these orbital diagrams, and also be able to explain the use of the Pauli exclusion principle, the off-ball principle, and Hund's rule. So we've already talked about principal energy levels and sublevels. Principal energy levels are made up of those sublevels, but sublevels can be broken down into even more specific areas called orbitals. So here would be our principal energy level 2-3 for boron, our sublevel, which would include, again, our letters representing the different sublevels would be 1s2, 2s2, 2p1. In our orbital diagrams, we're going to actually be showing the different spins of electrons and how those orbitals get arranged within sublevels and how the electrons get arranged. So an orbital is a region in which an electron of a particular amount of energy is most likely to be located. Remember, orbitals are based on probability. So the size of the sublevel determines the numbers of orbitals within them. So an S sublevel always has one orbital, a P sublevel has 3, D has 5, and F has 7. And each orbital can only hold up to 2 electrons. And you're going to see that the electrons are represented by arrows, and they are spinning up or down, and this represents, again, their spin. So each line can only ever hold 2 electrons. So like you saw on one of the first slides, this sublevel configuration, we're simply going to illustrate now showing those electrons and where they're placed in each individual orbital. So the 2p1, I just have 1 electron in the first orbital, because remember, p can have 3 orbitals, which are represented by these 3 lines. We can either use lines, or we're going to see at the end, we're going to use boxes, and those each represent an individual orbital. So 3 principles that we have to follow when we're writing these orbital diagrams. One is the Pauli exclusion principle. No more than 2 electrons can be in any given orbital, and if the orbital is filled, they have to be spinning in opposite directions. The off-ball principle, electrons occupy orbitals of the lowest energy available. So this is considered like the build-up principle, that we can only start to build them up as, again, we fill the lowest energy orbitals first. In Hund's rule, when filling orbitals other than s, electrons are placed in individual orbitals before they're paired up. And we're going to see that happen in especially any of the p sublevels, or if we were to get to a d sublevel. All right, we're going to use the grid. Again, each box over here is going to represent an orbital. Remember, each box that represents that orbital can only hold 2 electrons. So our expanded electron or sublevel configurations for helium is 1s2. That means we have 2 electrons in the 1s orbital, so we're going to place them with opposite spins. Beryllium has 1s2, 2s2. So again, 2 electrons are going to go in 1s with opposite spins, and the other 2 will go into 2s. Carbon, which has these 2 additional electrons in 2p, that's where we're going to follow those principles. So we fill in our first 4 electrons. Our 2 electrons in 2p, we're going to place the first one in the first orbital. However, instead of pairing them up, we're going to place them in individual orbitals. So the second 2p electron is going to go in a separate orbital. Oxygen, which has a 2p4 at the end, we're going to fill in again individually first, and then the 4th 2p electron is then going to be paired up in that first orbital. All right, and then finally with neon, we have 2p6 at the end, so that means we're going to have a full set of 2p orbitals, filling them individually first, and then with opposite spins, doubling them up. Okay, and then here we have a little bit of bigger configurations. Aluminum, we're going to basically quickly fill the beginning orbitals, so 1s, 2s, 2p, because we've demonstrated that on the earlier slide. And then as we move on, 3s2 has 2 electrons. We're going to fill those with opposite spins. And then 3p, the 1 electron is going to go in the first 3p orbital. For phosphorus, we're going to put the 2 electrons in the 3s orbital. And then the 3p has 3 electrons, and again, making sure that we put them in single orbitals first before doing any pairing. All right, so I would just take some time, review those 3 principles, make sure you understand them, and can relate them to the examples that we did at the end. And we'll be spending class tomorrow drawing these diagrams and also interpreting them and discussing how the electrons are arranged around the nucleus.